So let's start. So for me, it's a pleasure to introduce Fernando Buitrago, which I'm supervising in collaboration with the Greece Consuls in Nottingham. So he has been here for a few days. Well, last week, no?
1 week, yeah.
1 week, and now he will stay a few days more working
like a dog. Hopefully.
Enjoying parties. So. No, he will present today a few words about what he's conducting on his thesis in Nottingham.
Thank you very much, Nacho. So I suppose that most of you are familiar with this topic, as Nacho is here, and I suppose he told to you a lot about this. But I'm going to present you my personal point of view about the topic and the current state of art on it. So just for introducing you in my mind, for what reason they are interested. You know, when we look at a picture like this, for example, big gold cluster, our attention is drawn towards always the big objects. Nobody look at what is this tiny bit in principle. So what we want to know is what are the big monsters that dominate all the environment. But first of all, and first that speaking about the main part of this talk, I want to say a couple of things. First one is I'm very pleased of being here with you because I was a student in the master and I feel like it's kind of my home, and this is the first time I'm giving you a talk here. And in the other hand also, just a word about, you know, all of us are committed with the current situation of science in Spain. You know that for me this topic is a little bit more important as my supervisor is a Ramon and Cajal fellow. And we have to support them as strong as we can. But no more, because, you know, a lot of words being said about it. So the index of the talk is going to be this way. As I told you, first of all, I'm going to make you a little bit introduction about for what reason these objects are interesting. Secondly, I will describe you the whole problem and with all the different approaches are taken into account. And then I will show you the solution that my thesis presents on that, which is to work with the deepest photometry up to now, with the GOODS NICMOS Survey, and also working in 3D spectroscopy, with the final words of the work I'm doing here in the IIC these days and the final conclusions. So, first of all, for what reason are these objects very, very interesting ones? Well, here I say, this is the only things we can see in the high-redshift universe. This is not completely true, because you know that we have something that is very, very star-forming. We can see it very far away. But as you can imagine, as we go farther away in redshift, the objects we can see are only the massive ones, because we expect that the less massive are fainter. Apart from that, we know that as they are massive, they must drive all the environment around them. And they have related with these massive halos that start collapsing apart from the CMB. And then in a hierarchical universe, as lambda CDM scenario predicts, these small disks were clashing together and merging and form at the end the big spheroids we can see in the local universe. But the thing is, these spheroids are so different than the high redshift galaxies, the massive ones, that we think that we are losing an important bit on our understanding of galaxy evolution. To constrain my talk a little bit, I'm going to say that massive in this talk means stellar mass greater than 10 to 11 solar masses. And high redshift is something that is set greater than 1.5. And apart from all the things I said, to explain a little bit more, one of the big things we saw about they are different, it's this, the densities. We find them. So the number densities, we know that for the less massive objects, we know that there is a problem of the missing satellites. But also, we have the same thing in the simulation for the very massive ones. So depending on the model, we have different number densities, even of the order of 100 less. So this is very passive. But all the attention was in the last years about the sizes of these galaxies. So here I show you the plot of the effective radius, which is, as I suppose most of you know, the radius which contains half of the light of the galaxy. The same half-light radius for the galaxies, the massive galaxies in the local universe. This is redshift. And as you can see, let's see if this works properly. Here. We have a clear trend towards smaller sizes, both for disk and for spheroids. This plot I'm showing you is the biggest compilation of massive galaxies at all redshift, because here we play with the paper of Nacho and collaborators in 2007, and here this is our GOODS NICMOS Survey. So in total, here I'm showing you the results for more or less 1,000 galaxies, and this range spans for 80% of the life of the universe. And strikingly, the sizes are completely different from here in the local universe than here. So the growth factor is 5 times smaller in high redshift universe. So what's going on? And if you do a further exercise and you try to compile the densities of these objects, they are the same for both disks and spheroids, because you can think that although disks are bigger usually than spheroids, they have only 2 dimensions. So the 3D densities are both the same. And the numbers for them are, sorry about that. And the densities are comparable to present-day globular clusters. So the physics in these objects, it's completely something new. As you can imagine, when people look at these results that started in 2005, 2006, they say, well, there's something wrong in our measurements. So the thing they did were to try to make a series of work telling that we take into account PCF, we take into account the quality of the images, everything. And they said that the results were consistent. So, for example, the most comprehensive work by that time was by Trujillo and collaborators. And then this picture was reaffirmed by laser renditions with deep stacking of a lot of galaxies, with wide-field camera 3, and with adaptive optics, among many other papers. So here, I want to show you, for example, the typical picture with adaptive optics of one of these spheroids. As you can see, 1.8, and the stellar mass is 4 times 10 to 11. A big monster already in place at redshift 2. And all the galaxy here is just contained in 1 arsec. Something incredible. So, okay, so the sizes are wrong. Indeed. No problem. Yeah, it's very dependent. Well, we are taking the typical parameters of W map. Well, we think it's mass dependent. Up to now, there is not a comprehensive paper on that, but yeah. That's the good thing of having your supervisor in the same talk as you. So, okay, so sizes are wrong. If sizes are not wrong, let's say that masses are the ones that we cannot trust. But there was a comprehensive work about massive by Massin and collaborators that they say that you have to change stellar ages or you have to change metallicities by a factor of a lot in order to have completely wrong results. So the only thing that can affect a lot in our mass measurements are the IMF. But up to now, working with typical Chavrier IMFs, we think that everything is more or less okay, and these are the massive wave retrieve. And also it's confirmed by a paper of Nacho and Javi Cenarro, in which they found velocity dispersion that are similar to present-day massive galaxies. So if there is a change of mass, it shouldn't be very big. And apart from that, okay, if the masses are more or less the same, we think that IMF should be the same. It's what this paper said. But to me, one of the most proofs of this paper, in which they present mouse here. They present the densities, the stellar densities for this object in comparison with local galaxies. And as you can see, may I remind you that this is a logarithm plot, that the outskirts of objects are completely different. So this is very beautiful check of this object has to grow in an inside-out growth, in the sense that they have to accrete, as they are the drivers of their environment, a lot of minor objects around them in order to constrain, to build through redshift an envelope that is the one that starts with the big sizes they look like in the present universe. While at high redshift, its objects, here it is. So while at high redshift, things in the outskirts are completely different. And the densities in the center, both at high and local, and the local universe are similar. Okay, there would be a factor of 2, 3 different, that then we can explain it by the relaxation of these objects through redshift. So, okay, these are the lessons we can learn with deep photometry. Next way of trying to addressing this is to go for photometry. But then here we hit with a big problem of redshift, in the sense that it's extremely time-consuming to have reliable spectra of these objects. And for reliable spectra, I mean to try to characterize in the right way the absorption lines of the objects. So that was done, for example, in this work of Cimati and collaborators, and here I showed you the stack spectra for 20 objects. No, okay, the velocity dispersion, what I said before, it was related also with this work. In fact, it's taken with this spectra, this spectrum. Spectra. These are 20 galaxies, and in total, little, very little. Say that there are few tens of objects. And the measurements of the velocity dispersion were done with a stack spectrum. So I think that there are only 2 or 3 objects which you can see the velocity dispersion just with individual spectra. But if you take, for example, this work in only just one object, they claim that it's 500 kilometers per second. So always it's towards big values of the velocity dispersion. And well, Luis' PhD is going to be based also in measurements of spectra of massive galaxies. So in 1 year you have here the boy that can say you a little bit more about that. But the important bit is that, okay, if you take this value, that more or less is an agreement between the most of these other works, what you have, it's a value that goes about 200, 200-ish. That it's in agreement with a scenario in which the merging, I don't understand this mouse, so sorry about that. So the thing is, this is in agreement with a scenario in which merging is the most important driver of the evolution of these galaxies. So I'm going to explain to you a little bit more about this, this merging character, because in my opinion it's important. So how you can create something that is much more bigger in the local universe. Okay, the first idea, it's merging. So you take these galaxies, they merge together, and they have the big spheroids. So the typical lambda CDM scenario. But present rendition, something of the order of 2 mergers, sufficient to explain the whole evolution. So if this is not possible, the people say maybe there is an AGN contribution of these objects being so massive, creating a puffing up scenario. That means you can expel of the gas from the center of the galaxy and then create these envelopes around them. Now, also could say a little bit more about that, because he's trying to prove up to what extent this scenario could be true or not. But most of us think that the most important thing is this minor merging to create this envelope around the galaxy. So, for example, here you have the words of Carlos last year here in ISIN, his thesis, in which he tried to prove the best as possible, because really means minor merging, something that is very faint, something that is very, very tiny, so very difficult to peer with the current imaging. And they try to constrain this scenario very cool. So this is the evolutionary path that this galaxies has to follow. So the next natural question to that is, okay, where are these galaxies in the present day? Well, these galaxies are not present in the present day universe. So here the only thing we see are big spheroids. But as I showed you previously in the plot, we see a mixture of disks and spheroids with completely different sizes. So the people say, okay, these galaxies should be contained in most massive galaxies in the local universe. So, for example, we have the Sauron data in some cases with the cores that completely moves in a different way than the envelopes. That could be an minor merging around these galaxies. Another AC group, it's now the biggest, trying to work on that. So here we have the work of Ana Ferré and other people of the group trying to see the few really compact objects we have in the local universe. So in the entire Sloan, they only pick 29 objects with stellar densities not exactly the same, but very, very compact. And more work has to be done on these objects. And at the end, we perform also a work with Elena Ricciardelli, that is here also, about where these galaxies come from. And we try to link them with the submillimeter galaxies. Submillimeter galaxies are a galaxy population present at high redshift that they show an incredible big star formation, from 100 solar masses per year to up to 1,000. So with this star formation, so being very massive at high redshift and with the densities they have, we think that they are the possible progenitors of our massive galaxies. But things are not exactly matched, because, for example, in our work, we see lots of disks, while, for example, Swinbank and collaborators in Oxford University, they see in their images more spheroids. What we claim in the paper is what you have to do, what you have to have at high redshift is disk, then a merger, and then an spheroid. So maybe we can put everything together in the same box. But still, a little bit more work has to be done with the new HST surveys. So, for explaining to you a little bit more about that, here you have the images of the work of Elena Ricciardelli, which you can see. Mouse. Mama, what a talk. Here you have something that is consistent with to have this, something more compact, and a lot of merging. that it's consistent with this very star forming because there is a big merger going on. And apart from that, the work of Lisa Black, I told you before, that the merging, even the major merging of massive galaxies at high redshift increase. And the work we've done that we yet not published in Nottingham about the Corminder relation of massive galaxies, that it's consistent with the findings of Lorenzo as well, that she presented the other day, her thesis last week. So here you can see that maybe for the large objects, there is only an offset of luminosity. There is a change in the relation. And apart from that, as you can imagine, a lot of theoretical works done on that. For example, we have here was here from the University of trying to constrain this evolution of the velocity dispersion and the size of these galaxies. And the last works of Thorsten Knapp and Stijn Wicks about this scenario of minor merging. It's possible making exactly the counts and telling that everything is true. And one beautiful prediction is that you have to see blue cores in comparison with the outskirts for these objects. That it's completely something different that one would expect. And there is a pioneer work about the Argyll collaborators, and they say that they look at something similar, but it's not exactly true. Also, and much more to from our group and from different groups all around the world. How we address this problem? Well, we have in Nottingham the largest survey performed with HST in Europe. That is the GOODS NICMOS Survey, and it is the near-infrared counterpart of the GOODS fields. So to explain to you a little bit, NICMOS 3 camera to have the bigger area as possible in the H band for a total of 60 pointings, 3 orbits each, and with the exquisite quality of Hubble Space Telescope. Pixel scale of 1.1 arcsec with a PCF of 0.3 and a magnitude that is and limiting magnitude that is 2 magnitudes fainter than the best ground-based observation up to date. And the complete limit is as good as 10 to 9.5 solar massive at redshift 3. And survey we select, thanks to the work of our collaborators, 8 galaxies previously confirmed in the range of greater than 10 to 11 solar masses, and at in the redshift range from 1.7 to 3 that were classified before as BCK galaxies, extremely red objects, and distant red galaxies. So here you have the pointings of our survey. As you can see, it's not something continuous because we tried to really focus on massive galaxies. So the number of massive galaxies per pointing, that are the red squares, the black squares. Yeah, the black squares are the pointings of our survey, and they are optimized in order to maximize the number of objects in the GOODS field. And here you see examples of our sample. Here in the left-hand side, you have the ACS imaging that corresponds to ultraviolet res frame, while in the right side you have the NICMOS image, that imaging that is B-band res frame. So ultraviolet and optical. And as you can see, the objects really disappear sometimes in the ultraviolet, while the best way to characterize them, it's in the near infrared. If you want to have a deep look in our images, everything now, it's published on this web page with a list of all the works we carry out in Nottingham about them. And let me say only one word more about that. One criticism we have when working with massive galaxies always is that, as I told you, sizes are not real, blah, blah, blah. And in our images, as well as we can see objects that are incredible, such as, for example, for example, this asteroid that has 2 times 10 to 11 solar masses, and it's extremely, extremely compact, as you can see. Here, in the bottom, we have something that is very big. So we look, at the same time, things that are big and things that are small. But on average, massive galaxies are compact. And this is our point. So, exactly. Here, for example, in this plot, we have in our sample 80 objects. Here, the 3 we have in the top are 2 spheroids and 1 is very compact. But here in the bottom, I plot this one to show you something that it's big in our image. And here this is a 2-millimeter galaxy. Exactly. Indeed. I'm going to explain to you a little bit more about that, of course. So before going to that is related with this plot, I'm going to show you. I'm going to say to you a word about the environment of these galaxies, because here I'm going to present only the last papers. As you can see, the bibliography about them it's very, very wide. So it seems that there is no correlation environment from the work of Ruth Kruzbach and collaborators. Here, sorry for that. Local densities versus redshift. And the red dots are the massive objects. They are spread all around the plot. And here, you have the effective radius versus the local density. And again, there is no clear correlation. About the star formation and about the possible reddening, here you have the reddening we have in our galaxies. The massive objects are the big dots in the plot. Okay, and the rest of black dots are all the galaxies in our sample from redshift 1.5 at a masses greater than 9.5. So in our completeness limit. And if I remember correctly, yes, the red crosses are Julius. And as you can see, most of our galaxies are from left, always something that is very dusty, because are located in the upper part of the plot, and they show red colors, they are very massive, and they are very star forming. So what we think is there are a lot of dust obscuration in our galaxies. Exactly. But some of them could be red, as some groups said that they are red and dead. But most of them, we think that they are very, very star-forming objects. That because of the dust, they behave this way, and that's why they look always in this study very red at high redshifts. Sorry, say that again. Well, but the thing is, we did ourselves the massive. We take everything into account. We have dust in our mass compilation, so when creating the mass. And okay, things could be a little bit wrong, but mm-hmm. Mm-hmm. And I'm going to say the other thing you are going to say in the next slide. That's why. I suppose the near infrared bump. No, okay. I thought that Nacho wants to say it's, well, is this plot. sorry for jump into another slide, but we constrained also the CIDs of our objects with far infrared. So what we want to do in our studies is, okay, if this is dependent of the star formation, let's try to characterize it in a holistic way. So for example, the work of Amanda Bauer is done with Spitzer and ACS imaging. We go also for different facilities. Only more about Spitzer work and typical infrared star formation. So one thing that amazes us very much and puzzles us very much about our sample is this plot, the top one. As you can see, the star formation from redshift 3, it's constant. Not only, but to galaxies of all the possible masses. That for massive galaxies, LIRIS imaging of massive galaxies looking only at H alpha. Is quenching the star formation of this object. It's something that is acting very, very quickly, because we are retrieving big star formation for our sample at all redshift from 1.5 to 3. One pioneer work that, in my opinion, was not read a lot by the community is Pablo Pérez González and collaborators, in which they took the sample of Trujillo 2007, and they take these 800 galaxies from redshift 0 to redshift 2, and they try to look at the MIPS detections of this object and derive star formations. And what they say is most of the objects, and the percentage is bigger, as you can imagine for these, are very star forming. What we did with the GNS, with our GNS, it's to try to go beyond Spitzer. So for example, here we present results in the top of Marco Vieiro and collaborators using and La Boca. And stacking all the images, what you can see is that these galaxies are very star forming, and these are very, very clear detected what the star formation are more modest. Of the orders of 50, 100 solar mass spectra. And this was further tested by Antonio Cava here in the IAC with Herschel, the recent launched satellite, in the Hermes survey, and you can see there are a lot of detections with the Spire instrument, and that are the color dots. And the typical star formations you retrieve are something very big, something of the order of 100, 200 on average for the entire sample. So maybe other groups are right, and there are several red and dead objects, but we think that most of them, for all this set of proofs, are star forming. And this size evolution is not correlated with the star formation or not the star formation of these objects. So part of my work was also in trying to characterize them spectroscopically, and to do something different than the other groups, and only to try to really understand the kinematics of these objects, in the sense that being so compact, how it's possible to happen in these objects. We've done the majority of you are with this method, but if I'm only going to say about how it works, that you take your field of view, slice it, and put the different slides in a bigger, slit that you can spread out with grease. And then with computational work, you can rearrange all the slides to have the image of your galaxy, and also at the same time to have the spectral information. That's why it's called 3D spectroscopy, because at the same time you have the x-axis, the y-axis, sorry about that, and then the spectra of every different pixel. So we went to VLT and we used the SINFONI spectrum. Here I said bright future because you know that VLT instrument, but the next generation one, CMOS, is going to arrive very soon, and nowadays more or less Every telescope has one of these instruments. For ELT, it's Plan, Eagle. And apart from, try to have the spectral information in every pixel, the beautiful thing is velocity. So in my work, the data validation is off, and now we are trying to model the data to try to have accurate rotational velocities, velocity dispersions, because you know that seeing the velocities here affects our measurements, and we have to go object by object looking at what we can exactly retrieve about them. The point of this sample is all of the galaxies are all selected by stellar mass, with masses greater than 10 to 11 and a redshift of 1.4, because as I told you before in the talk, spectra are so difficult for this kind of object that you have to go to a smaller redshift to try to look at something. But even this way, what we can see are only emission lines, only H alpha and H2 for our sample. But the beautiful result is for all of our samples, we have detection. Maybe not for all of them we can have real kinematical maps, but we see continuum in all of the objects that really nature of our galaxies. So here what I plot is one image. The color pixels are, while the contours show us the we don't know exactly if we are looking at the exactly kinematics of the galaxy. And as I told you, more work has to be done on that. Here I only want to show you a couple of plots showing this. And the velocity dispersion of our objects. You can see the values, for example, here range in rotational velocity from plus 100 to minus 100. The velocity dispersion are of the order of 115 kilometers per second. The same one for this object, and as you can see beautifully here, we have something that is clashing with the. Mama, when I'm gonna understand. And alpha emission is more extended than the continuum of the galaxy. And again, the same, more or less, the same parameters. And the problem of retrieving these typical parameters is that if you calculate the dynamic, smaller than the stellar mass. So the only explanation about that is that spectroscopy measurements, we are only mapping exactly the behavior of the gas. And this is adopted with papers, for example, with SINFONI Survey, with Natasha Forsyth-Steiber, Reinhard Genzel, and all these people. A little bit more of work has to be done on that, and the exact modeling, it's going to come in 2 weeks' time. So we will put a paper about that. But I think that, yeah. Mm-hmm. Exactly. The only explanation is you are looking only at gas. In principle, but not exactly, because imagine that these objects, as we see, as we said before, they are clashing, but they are merging with minor objects. So one will expect that you have something that it's start forming the outskirts, but it's not so, not this way in the center. So fans of stars or I have to show you I have here the data in the papers. I can't remember exactly the typical value. So it's not that. That's the thing. So there are a lot of different possible behaviors. As I told you before, for example, in the theoretical works, they say that in principle the cores should be bluer than the outskirts for some of these objects. So we have to have a clear picture of them. A paper I really like, these galaxies are not so massive. It's with, again, with the German. But the thing is, they point out things at redshift are much more clumpy and much more turbulent. So maybe what we see, it's kind of a galaxy with the images we have. But if you have here, for example, NICMOS true observation with 4 orbits per object, what you are going to have is something much more clumpy. Also, to have an idea whether that is true or not with the data we have in hand, I'm working these weeks with Nacho about how is the morphology of these objects. So because up to now we only said, okay, the search index is this way. But here I want to show you this plot in which, only taking search indexes into account, there is an incredible trend about spheroids are more scarce at high redshift, where there are much many disks. And if we believe in the lambda CDM and in this hierarchical scenario, these disks are crashing one another and merging to create the final spheroids in the local universe. So we are also going to put the 0 point in the local universe using Sloan data that Jesus Varela is helping and working us on that. And also, we are going to do that in a visual way. So here you have the same plot as before. Well, I have to admit that at high redshift I add up the search indexes. But we are trying to characterize that visually using galaxy data, also in the local universe. So trying to have the things that are cutting edge right here, right now. So only to give you the final words of this work. Massive galaxies could be the perfect bed to try to understand lambda CDM, because their strength properties can tell us a lot about how things are going. I talk about the extremely small sizes, Trujillo 2007, Buitrago 2008 papers, that we characterize them with the largest sample up to date. There are lack of these galaxies in the present-day universe, but if you want to know a little bit more about that, go to Anna and to her work. And they show a variety of star formations. So we have to try to know exactly which objects we are looking at in every different case. This trend about things in the high-redshift universe are much clumpier and are characterized by this seems to be clear, and we hope to put a letter as soon as possible about that. And if you want to try to know a little bit more about that, for example, Canarias data that is going to appear next year with 12 orbits of Hubble Space Telescope per pointing, gonna say us a lot about these objects. Thank you very much for your attention, and happy Christmas.
Any questions or comments?
My dear friend.
Sorry, I am.
No, I'm very grateful to you to ask as many things as possible.
A very nice talk and very nice topic. And it seems that the problem that you put at the beginning, one of the things you mentioned is how to stuff, to make these compact things, to have them into bigger things nowadays. To me, well, that is an interesting issue, but well, no?
Keep going, please.
But one question which to me is important is how to be able to form such a large number of stars with such a high star formation with such a small thing without destroying the system. So this is another question that I think has to do with all possible modelings, not only of evolution of galaxies with merger or blah blah, but also with the mechanism of star formation feedback. And then it is clear that you want to keep, to form, to trigger, and then to maintain all this mass together without destroying the system or losing the material by winds or whatever. You have to be very extremely efficient forming stars. So you have to get into a mode which is called positive feedback system. And then this is something that you should somehow consider for the understanding of this system, and not only the modeling of this system from their compactness to nowadays, but also how to be able to trigger and then to maintain such a massive system with such a high star formation density in this time of the universe.
The triggering seems to be something that is proven in the sense that if you class a big disk in the high-redshift universe, you can have a big star burst. But Kausiana, you are the person who knows a lot about it.
No, it's just something that it is interesting. We can discuss about, but I mean, the number of topics that come together with this, with your talk. But one very basic one is how to be able to trigger star formation. Imagine you are able
the problem
to
maintain it's very interesting because I showed you the of Amanda Bauer. That, by the way, I think he's looking at us from Australia. So, yes, the star formation is maintained in this range, from redshift 3 to redshift 1.5. So that means 2 gigayears. And this time scale is very big. Also, the problem we have is, if you look at these galaxies in the present day, the star formation is 0. So there should be, you said, this positive feedback that maybe can act for a little bit, but also there has to be a feedback that it's able to quench very efficiently these galaxies. And this is not understood at all.
Yeah, that's very important. But really the number I had in mind, not just the total star formation rate, which, as you said, has a large number and now is small, but also the star formation, the specific star formation rate. So it is very huge because you have a small volume. And what I'm thinking about is that you have very high star formation density, and therefore you have a very high energy input from the stars that you are forming. And then you need to be able to reuse this material, otherwise you are going to blast the system in such a small volume. So that's what I mean by positive star formation. That means that you are forming a lot of stars in a small volume, but you are somehow escaping the negative feedback produced by the stellar winds coming from the stars, which are going to tend to destroy the system. You have to be able to keep everything together.
And how could that affect to our results, for example?
Well, I have some references. I will not. It's just something that I will.
Thank you very much. Be kind, eh?
Yes.
Hi.
Have you compared the star formation rates from H alpha from your 3D spectroscopy to the infrared ones?
The problem is I haven't gone through that yet. So my aim is to characterize the kinematics. Star formation will mean that, to have the flux calibration. That it's easily, you can do that easily, but it will take a little bit of time. So up to now I'm focusing only in the kinematics, and maybe one further step will be that. But you have in the bibliography, for example, the works of Benoit Pinat, that the problem is these galaxies are not so massive. But in all the 3D spectroscopy works, or at least in the majority of them, you can have the star formation of these objects.
Yes, the question is, it's related to the so high star formation rates that you find from the infrared.
Perfect.
Because, for example, I'm studying more or less the same, but with the slit spectroscopy at redshift 1, and what we find is that the star formation rates from H alpha are even corrected for extinction, are so different from the infrared ones. So, of course, you are losing the totally obscure star formation with H alpha, but also when you compare all the UV star formation rates, infrared and H alpha ones, star formation rate indicators, you could see that some, not all, but not star forming, not very young stars are hitting the dust.
Hitting the dust. This could be an issue.
So what I find is that maybe between 20 and 40% of the infrared luminosity could be due to this heating from not new stars. So maybe one of the reasons of there are not so high star formation rates at this redshift, but it's something that it's very difficult to check.
I will have a look on that because it's very interesting, and this is really a problem we are facing. So, for example, I spoke a little bit, you know that there are Fernando group in USA that what they say is they have a sample of 10, 20 objects, and most of them they don't show H alpha at all, or very, very little. So how is that possible that at the same time I'm talking to you about high star formation and no star formation at all? Or, as you said, if you take ultraviolet and you take near infrared, there are a lot of scatter into the star formation. So we think that this pocket of star formation contributes a lot. But as you said, maybe it's not the only reason for these galaxies. They look like different than in the present day.
Okay, thank you. And sorry, one more question, the last one. So, are you able to see if you have very low brightness at the external parts of the galaxies, are you able to detect these stars at the external parts at these redshifts?
Well, the thing is, according to our imaging, we think that if losing light, we are losing very little. I don't know exactly what you mean. I suppose that you mean that if we can see this star formation kind of dots or nodes all around the galaxy.
To the photometry? To the photometry that in the local universe you are comparing high redshift galaxies to the size of local universe galaxies.
Okay.
So here we can see a lot, brightness until a very low limit, and at high redshift we are losing that part. So
we are losing that part, but we think that with our extremely nice photometry, think that we are, for every galaxy, we have 3 orbits with Hubble Space Telescope.
Okay.
It's the best we can do up to now.
Okay.
We think we can really assure you that the galaxies look like this way, and about all these different works, we really think that they are massive and they spread out to this distance. Because if they exist, as I showed you before, several images, we can see also things that are very spread out.
Okay, so do you know what's more or less the percent of the galaxy that you could be losing compared to local ones? No. Okay. None. Local ones? None. Okay, thank you.
Just to point out, you mentioned that for the 3D spectroscopy galaxies you found a lot of rotation. And these were galaxies with masses on the order of 10 to the 11 or more.
All of them are greater than 10 to 11.
So I just wanted to highlight the fact that these are truly remarkable, guys, because they're not just in the morphological sense, they are much more compact, as you've shown. But
only one thing. The sample in SINFONI, they are selected by mass, not by compactness. We have several proposals up to now focusing only in 3D spectroscopy of the real compact object. But these galaxies are only selected by mass, and they may be compact, they may not.
Well, in any case, the interesting part is that for galaxies, if you go for the local analogs, none of them rotate at all. And the fact that you find a lot of rotation in these big galaxies makes them quite unique compared to the local galaxies of the same mass.
In that case, 2 things. First, I'm looking at Sauron results in order to understand exactly why this is the reason. But maybe, my expectation from the photometric point of view is that 50% of the sample are disk and 50% of the sample are small.
Yeah, I'm not arguing about the result. I'm just saying that they're truly unique. I'm trying to emphasize the fact that I believe these objects are truly unique.
I hope they are not so unique and they are real somehow.
I want to emphasize on this plot because still it's not clear what is the meaning. I mean, it's clear that today, if you take objects more massive than 10 to the 11, you can see the trends very clear there. These objects are typically elliptical galaxies. No? Nobody will be surprised about that. But if you follow that trend, you can see that the objects that look spheroids are decreasing and decreasing and decreasing, and what you see from the morphologies is that they look more in appearance like this galaxy. So that doesn't mean directly that these galaxies will be transformed into the spheroids. Okay, so because we don't have the number densities, it could just be simply that this galaxy remains constant, and there's something new that is creating new spheroids, for example. So until we have the number density evolution, we cannot say which thing is being transformed into the others. And the clear point here is that if you go to the high-redshift universe, the typical object was a disk-like galaxy, or it has a low Cercic index, more close to an exponential, and it has a larger ellipticity and so on. So it's very interesting because the prediction from the London CDM scenario is that the first object to form the most massive galaxies are disk-like galaxies. So I think this is a very nice trend. And what Fernando is doing, and it's so interesting, is that he's trying to confirm kinematically whether the reality of these photometry results are true or not. So. Mm-hmm.
One more question, one comment. Asking about metallicity, could you say something about the metallicity of this? But you have a spectra.
There should be something, I suppose, in the spectra works, but I'm sorry, but I cannot say to you nothing.
From what has been published so far, I mean, the spectra from the group of the Netherlands group and so on, very low quality. Well, I shouldn't say this international. Well, that spectra suggests that the metallicity is solar at the redshift. But they are very big, and they are already. I mean, these objects are typically 2 billion years old at redshift 2, so they are already old.
It's only one last thought as regards with what Jesus said. So, if you take previous works, all the people tend to say that as you go away in redshift, as you go to higher and higher redshift, things are much more clumpy and much more disk-like than the present-day universe. But the thing is, and I think that this is the real power of massive galaxies, this galaxy population is so special, has this feature that make them such different, that I think that it's very easy to try to test lambda CDM only looking at them, because you can constrain them very, very easily.
Okay, can we thank Fernando for a very interesting...